Okay, so like I said, I've been meaning to do this for a while. Like, by verify, I mean, like, here we didn't know this ahead of time. When you just had this, you have no way of guessing. But when you're verifying, literally just plug it in and see if it works. So I am going to indeed square both sides here. The x, if I square it, I'll get 1 minus t squared, 1 plus t squared, all squared, plus 2t over 1 plus t squared, all squared. Which is, now we're going to have a lot of firsting, outering, entering, and lasting. And I notice that that's going to give us a common denominator. So I'm going to just go ahead and do that in one step and say, well, when I square that out, we'll have the common denominator on both sides, so let's just do it. Well, first outer, inner, last on the bottom here is going to give me a 1 plus, how about 1t squared, another 2t squareds. Finally, t squared squared is t to the fourth. So up here, now we have first outer inner last gives me a 1 minus t minus t squared minus another t squared gives me a minus 2t squared. Square a negative and you get a plus, so plus t to the fourth. Plus is the thing in between. And so we have 2t squared gives me 4t squared. These guys come out to 2t squared plus t to the fourth. That and that give me a 1 minus 2 plus 4 is plus 2 t squared plus t to the fourth. Indeed, right? So one thing you could have done, like, but actually no, because I told you to solve for t and set them equal to each other. But if I just said, here, figure out what that is, t, you know, give you a domain for t, you could have said, well, I don't know, let's just try a few things. Maybe if I square it. And if you squared it, lo and behold, this happens. And so then you end up with this, and you'd be absolutely right. And that would be perfectly fine. Sometimes squaring things is really, you know, good. Okay? Anyway, I wanted to do that. And then I had, on this note, well, not on this note, on a slightly different note, I had a lot of stuff I wanted to say about something and realized I want to go in a different direction today. So maybe we'll talk about that other stuff next time, maybe not. I might not talk about it at all. It's not part of the curriculum, but it's really cool stuff. So I wanted to bring it up. Anyway, so homework, same section, 13 through 43, odd. There's two parts of this, and for numbers 27 through 43, it says blah, 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 blah. Use it to help you sketch the graph. Don't sketch the graph. We're not going to graph. You'll be doing plenty of that soon enough. And so this time we're going to focus on something slightly different. And so, here we go. Oh, there's that guy. Okay. So first off, okay, so recall the last time we did this. We said, you give me any point in the plane, and let's call it x, y. So you're at some point in the plane, x comma y. And we said, that's one way of describing how to get there. The other way is using polar coordinates. And by now you should be pretty familiar with this, right? We could say, well, it's some distance from the origin. We'll call that r. And if you're measuring from here, then we could talk about theta being measured from here. Theta, right? And so then in terms of this, how can we rewrite x in terms of r and theta? What is that?
Come on! Cosine of theta equals x over r.
Yes, okay, so that's how I'm going to think about that. If there's an x and there's a y, and that's theta and that's r, you told me cosine theta is what over what?
X over r.
Over r, meaning that x is equal to
R times cosine.
r cosine theta. Okay, now what about y? What do we do for y?
Sine theta equals y over r. Y times theta equals
Y over r, and so y is equal to r sine theta. Now, what is r in terms of x and y?
Square root of x squared plus y squared.
There you go, right? We use the Pythagorean theorem to say that x squared plus y squared is equal to r squared. And then if we want r just by itself, we take the square root, and it could be negative, because now you would get a plus or a minus, but and that does work because in your homework you've seen like I could give you the angle, say pi over 4, and then give you the radius of -2, in which case you'd go back in that direction, and that's perfectly good. But what we're going to do here is say, okay, take the positive square root to give you r equals the positive square root of x squared plus y squared. So you'll notice in this case, these right here that I've written, this is if you have an r and a theta, you could recover x and y. Now if you have an x and a y, here's how you could find r. You could also find theta by, and this one's not so easy because, as we'll talk about in a second. How could you relate theta to x and y here? What?
Tan.
Tan theta is equal to y over x. Okay, so this is what I'm going to put up here, and I think this is how they have it in your book too. It's y over x. Why didn't I write theta equals arc tan y over x? Well, because a couple things. Let's just think about this. What's theta if your point is right here?
90. Or pi over 2.
How about pi over 2? From now on, we're gonna do radian. So we would just say theta is pi over 2. And so, but what is the x value here? 0. Right. And so, but yeah, and if you were to think about being able to plug in tan of pi over 2, right, you'd have pi over 2. Here you'd have negative pi over 2. And so, yeah, you could say, yeah, divide by 0 should give you something infinite. It should blow up, and so it kind of does. But you're kind of missing the forest for the trees if you're doing this type of thing. If your point's right there, you could just say, well, if my point's there, it's pi over 2. If my point's down here, I would say it's what? What would the radian measure be? If we're measuring all the way around. 3 pi over 2. Okay, and of course it's also polar coordinates. So we could call this one, if this is up here, and has a radius of say 2. You could either call this point 2 comma pi over 2, or you could call it -2 3 pi over 2, right? There's a bunch of different ways you could do it. But if you're given either of these, you get that one point right there. So, but also, so this is also kind of tricky if you're outside of the first or the fourth quadrants. Because if you're in the first or the fourth quadrants, you use arctan, no problem, right? And so, but what if you're in the third quadrant? You kind of have to use your brain, right? So like if your x were here and your y were here, and let's just say that x was -√3 and y was equal to 1. So you're at the point here, -√3 and 1. And if you just plug that stuff into here, well, arctan would tell you, since you have tan theta would be y over x, so that would be -1 over √3. You plug that into arctan, and you're going to get, well, what would it be? That would be pi over 6, so negative pi over 6. But that's not where you are. You're actually in the third quadrant, so you have to use your brain, right? And the way that I've always talked about doing this is pretend that this triangle is just this triangle. And you find that this is pi over 6, so you know that this is pi over 6, and so theta is actually 5 pi over 6. But this one, I'm going to put a little star by this to like be careful. Don't take this as the gospel truth, because it'll work just fine if you're in the first quadrant or the fourth quadrant because of this right here. But if you're outside the first quadrant or the fourth quadrant, things are going to be a little bit different. You just have to use your brain. It's almost always easier to just draw it out. Anybody get that? Right? Any questions about that? Does that make sense? Okay, so we are going to use these heavily. But before we do that, we're going to break your brain. So equations up until now have usually been like an x and y, and if you have something like, I don't know, 2y equals 3x, and maybe we'll put an x over here plus 1. The name of the game has been to get one variable on one side and get the other one on the other side. And we usually choose y to be the thing that we're trying to isolate. So you get all of your y's on one side, all of your x's on the other side like this, and then you finally get the y by itself. And this is just by convention. They could have decided, you know, hundreds of years ago that we're going to do it the other way, where x is the thing. Whatever, who cares? This is just by convention. That's Cartesian coordinates, where x is the thing that moves exactly in this direction, and y is the thing that moves exactly in this direction. Now we're going to talk about equations in polar coordinates, where we have r and theta. And you might have a bunch of r's and a bunch of thetas and stuff, but the game's going to be the same. You want to get one of them by itself and get everything else on the other side. In other words, what you're looking for. And the thing that we want is r to be by itself. And then you want to get all of the things involving theta on the other side. So in other words, you're looking for the function that you're thinking about is the input is theta, and then the output is r. And so this is the type of thing we're going to be doing. We will be graphing these things, but not today. I'm going to tell you how we're going to go about doing that. But right now, we're not going to do that. Well, that's exactly what we're about to do, but for homework, we're not going to do that. So let's use an actual example here. Let's say that r equals sine theta. So instead of some function of theta, well, how about sine theta? Let's just start with r equals sine theta. Oh. Now, here's the thing. You might think, I could graph that. That's easy, actually. I'll just do this, and I'll just do this. Actually, give me a second. Give me a second. There's a method to this madness. You'll see why I'm doing this in just a minute. Okay, so there's that. Where's halfway? Halfway is right here. And you might think, okay, you know what I'm going to do? This right here. I'm going to say my input, obviously my input is theta. Obviously my output is r. And so I know, actually I wanted to do cosine first. Sorry everybody, sorry. See, like I said, I changed gears last minute, and so I want to do cosine. So cosine, okay, well cosine goes from 1 down to -1, and we know that it starts up here, it goes down like that, comes back up, and hey, I'm done, right? There's pi, there's 2 pi, we'll call this, oh no, there's pi over 2, sorry, pi over 2, here's 3 pi over 2, okay? Everybody, right? Everybody buy that? Like if I just gave you that, you could draw that, and you'd be absolutely correct. If we were graphing in Cartesian coordinates. But in polar coordinates, theta is not this line, is it? Theta is the actual measure of the angle. And r has nothing to do with this direction. R has to do with the distance from here. So we'll get to this in just a second. How are we going to draw this? What would a polar graph of this look like? Well, we have a method for that. And you will be employing it heavily in your next homework. And I want to talk about what that is now. Let's talk about what this graph is. Okay, so if you think about, one way to think about this is, okay, if I think about the output, the r, the output as being the value here, the height, right? I mean, that's what we've been doing forever, right? We think about the output of a function as a height on the y-axis here. Well, then what we have is something that basically it starts up here. You could think about it as a dot that when your time starts, or when your theta is equal to 0, it's the dot that starts here at 1. And as time goes on, that dot bounces down, right? Oops, now it's here at 0. And then the dot comes down to here, and then the dot comes back up to here, and then the dot comes back up to here, right? Like, you could even think about it as though if the dot just was right here, or you could think about the marker as being like how I'm going to draw this. And if I had a little like servo mechanism or some kind of like machine that just brought this thing down and then brought it back up, and it took a total of, let's think about this. Let's say that I'm moving 1 radian per second. So then after 3.1 seconds I'm here, and then it takes me another 3.1 seconds to get here. And if this thing did the same thing, it took 3.1 seconds to come down and then 3.1 seconds to go back up, then the picture I would draw would be this. It would just come down like this, it would drop down, and then just come back up. There's nothing special. Well, that's kind of special, but we don't have to do it right here. In fact, if I wanted to, I could just take this and say, here's your function. It goes like this. Start your timer, and so you start your timer, and it goes. And then after 6.28 seconds, it comes back to the top. Everybody with me on that, right? All we're doing is we're just keeping track of one variable here. We're keeping track of how high, or what is R, as time goes on. And yes, I know this is theta, it's not t, but let's just think about it as t for right now, right? And we could see that if I did that, if I had a marker that just bounced down once I start my clock here, and if I'm moving it 1 radian per second in this direction, or 1 unit per second in this direction, it would draw this graph. There's nothing special about that. I could have done it this way. I could have said, well, let's just move it this way. And then what would happen is, I guess it would draw a cosine curve. It would just look, this way. So let's use that same information. We're going to pretend that I have some machine that takes this, and once I start my clock, it comes down and goes back up, right? But now what we're going to do is do this in polar coordinates. And so, give me just a second here. I might as well use this here. And if that's, I'm going to do it this way. Do it right here. So now, sorry, guys. Just a minute. That looks all right. So now it's no longer the case that R is this thing when we're in polar coordinates. Now R is the distance from the origin, and theta is the distance. And theta is this type of thing right here, right? This as I turn it. And so we can imagine the same thing that we did before. We have this record, we have this machine that when I start the clock, it starts here at 1. And notice what I've done here. 6 right here was 0, right? The 6-inch mark was 0. And the 1-inch mark is positive 1. And so if I come down by the same amount, 11 is now negative 1. Everybody with me on that? I didn't blow anybody's mind by that, right? That's just, right? And so, well, what we're doing here is we want to find out, this is for theta is my input, but theta is the angle from here, as we measure from the positive x-axis here. And so, using the same record, right, I could say, well, I should be able to draw r and theta as long as I have the same thing that goes down, it takes a total of 6.28 seconds to go from here, drops down after 3.14 seconds, and comes back up after 6.28 seconds. As long as I take this and I just move it around at the same rate, right? So I'm going 1 radian per second, right? So then after there's at pi over 2 seconds, and then I'm going to go around and it'll be at 3.14 seconds, and then however many seconds, and then finally I keep twisting it around to get to 6.28 seconds. Then I will have drawn that thing, and it will be in polar coordinates now. And so that's what a graph of a equation in polar coordinates is. That's how we're going to define it, and this is what it would look like. And so I'm not going to be able to actually do this like as it goes, but and this will don't worry about this. Don't try to absorb all of this right now, because this is what we're going to do Thursday. We're going to go deep into how to do this well Thursday. But for right now, I just want to see what this thing would look like. So we know that it starts at 1, right? That the radius starts at 1 when theta is equal to 0. So I'm going to put a little dot right there. Oh, I'm running out of juice. Give me a second. Do it in pink. Okay, so when theta is 0, r is equal to 1, so I put a dot right there. And now we can imagine as this thing comes up, this goes down that way, right? And so the next point, let's do it this way. After pi over 4 seconds, I know that my theta should be here at pi over 4 radians. And we can see that right about there it's at, and I haven't drawn this like perfectly or anything, but it's about at 1/4 right there. So I could say, okay, so by the time it has gotten to here, it should be about here. I could put a dot right there. And then, okay, so it keeps going and time keeps going down. So really all that's happened is my dot has moved from here to there, right? Because remember, all that's happening is once you start the clock, this thing just moves down and just comes back up. And so I've started my clock, it moved down and got to there. Finally, I get up to pi over 2, and it's at 0. Okay, so what would that look like? Well, it might look something like this. So as this moves up, this thing goes down like that. Keeps going down as this goes, and it's not until it gets down to 0 that it hits right there. Okay, not sure if that should be kind of convincing that this thing looks like this right there. Now let's continue on. What happens after that? Well, as I turn this way, now it's the r is negative, isn't it? It's no longer pointing out that way, right? R goes from positive values, and once we get to pi over 2, it's there. But now it's coming down this way. And so, as it goes this way, it starts to come down. Oops, like this. Oops. Right, I'm not doing this very well. As you can see, this is really hard to do. I tried to practice this and did not have much luck. Well, what's going to happen, and again, we can take some points here, right? When it gets to pi, it should be at -1. So in other words, once we go from 0 all the way to pi, it should be back here at -1. When we're in between, when we're halfway, say in between pi and whatever, I should be at about 1/4 And so when it's down here, I should be at about 1/4 I should be right here. And you can imagine that if I did this well, it might look something like that. I did that terribly. But what happens is that this thing ends up making, and if I did this very well, it would look like a circle. Remember, what was the first value, right? The first value here The output value, the first value of r when theta was 0, the value of r is what?
1.
1. So that means when theta is 0, in other words, theta is measured this way. When theta is 0, this should be what? 1. And indeed, yeah, and then when theta was pi over 2, when theta was pi, it should have been a negative 1, which means instead of going that way towards pi, we go in the opposite direction, and yep, again, brings us back. And then it just would continue on, and then you would trace the circle around again. Now, here's the question. If this is indeed a circle, and it is, what would be in Cartesian coordinates, what would its, there you go, yeah, okay, so yeah, so in other words, I want Cartesian coordinates for the equation of this circle, and we know that it has a radius of what?
1/2.
1/2. And where's its center?
0, 1/2.
So radius is 1/2. Its center is, it's where?
1/2.
1/2, comma, 0. So what would, just given this, in Cartesian coordinates, what would the equation of that guy be?
Would be
1/2 square.
equals,
Okay, so 1/2 squared equals
1/2 square plus 0.
no, x.
1/2 squared plus 0.
Wait.
X squared.
You need an x and a y if you're doing, if
X
you're going to have an
minus-
equation.
Or x plus
Hey,
1/2.
X plus 1/2.
X minus 1/2.
X minus 1/2
Squared
squared
plus y squared.
plus y squared. I agree, right? Because we've shifted the center, and when you're doing it in the inside here, it shifts it in the opposite direction. So that should shift. That should be the equation of that circle right there. Now, watch this. So this will be, doing this first will be very useful when you actually go to graph these guys. But we're not doing that this time. This time, this is what you're doing. You're going to say, okay, well, if r is equal to that, and if cosine is that right there, there's two ways we could do this. I'm going to show you here. What you could do is say, well, hold on, I'm just going to replace everybody. And if x equals r cosine theta, then cosine theta is equal to what?
X over r.
X over r. But if r is equal to that, we could rewrite that as x squared plus y squared, like that, equals cosine theta. And so now we just replace everybody, and we could say, okay, the r on the left-hand side is the same thing as root x squared plus y squared. The cosine on the right-hand side is the same thing as x over root x squared plus y squared. What do you think I might want to do now? And so if I'm trying to turn this into something I've seen before, I could square both sides. That's...
Or you could multiply
You
those.
could multiply, you could just kill that denominator.
Yeah.
Then you won't need to square both sides. Because if I bring him upstairs, in other words, multiply both sides by this, by what's in the denominator, it kills that. And then it also makes this easier. Okay? Now what do we do? Well, let's try this. X squared minus x plus y squared is equal to 0. Now, how might we turn this into something we've seen before? In fact, I'm pretty sure you've had this exact problem last year.
Is it completing the square?
It's completing the square. And so, right, it's like if I could get this into x, pure x something squared, pure y something squared equals something, then this might be a conic section. And I might be able to write it like this. And indeed, that's what's going to happen. So we're going to complete the square on this guy right here. How do we do that? What do I need to do?
It's like, what is it?
We'll add.
So if the
1/2
coefficient,
x.
yeah, if the coefficient's -1, then what do I need to do?
Divide by 2.
Right, and then I do what to it?
Square it.
And I'm going to add that thing squared and subtract it squared. That way I haven't changed the equation by doing that, right? Now another way you could have done this, if you're savvy, you could just say, well, I'll add to that side of the equation and add to this side of the equation, which is how I said don't ever do it that way, because once you get in that habit, you will mess some stuff up later on in life. But I mean, if you're into that, you could just do that. You could just jump that step, right? If you know what you're doing, I recommend that you don't, because later on in life, it will be really good that you remember this nifty little trick. It's a nifty little trick right there. And so, but at any rate, okay, now that we've done that, the whole reason we did that was to turn this thing into a perfect square, which is what?
X
plus 1/2.
Plus 1/2?
Minus 1/2. Sorry.
X minus 1/2 squared.
Right.
All squared. Now we check it. Please, when you do this homework, check it, check it, check it, please. So we're going to first outer inner last this guy. First gives me x squared. Outer gives me minus 1/2 x. The inner gives me another minus 1/2 x. Minus half minus a half is the same thing as minus x. That's what we have. Nice. And then when you square that, you get a positive, that thing squared. So yes, okay, we're good. And so, lo and behold, it's the same thing. Oh, that's pretty cool. So it turns out this is what graphing in polar coordinates is, right? Instead of thinking about a graph as, so, I mean, in every case you're talking about a function, and a function just tells you, you know, the output. That's just, in our case, that's just one variable. How high or low is it? But now high and low is no longer the y-axis. The output of this thing is now the radius, and the input of this thing is now how far you've turned it. So as before, up until this point, all of the graphing you've ever done has been talking about, you tell me how high up something is dependent on how far right we've moved, right? And so what you get is the thing that draws as you go like this. Now what we're doing is, instead of saying, I don't care about how far right you've moved, I care about how far, what your angle is that you're making with the x-axis there. And so now, so that's just a different way of graphing, and it's interesting that this type of thing does this, right? Everybody get what we're doing? Okay. And so in your homework this time, you're gonna go either in one direction or the other direction. They might give you something like this and tell you to write it in polar coordinates, and the way you do it is just with these guys right here. Or they might give you something in an equation in polar coordinates and tell you what is the thing, like find the object in Cartesian coordinates. So one way or another, you're either going one way or the other way. That's what you're going to be doing. Questions? Okay. So your book does some. So let's go in the opposite direction real quick. Let's say we're given something in Cartesian coordinates, and we want to find it in polar. Your book does this. Your book says, find the polar equation of an arbitrary line. And this is not a problem. This is an example they give. This is on page 872. On page 872. This is example 3. And it says, find equation, I'll say polar, find polar equation of arbitrary line. And then what your book says is that the equation of an arbitrary line is
Y equals an x.
right? That's what you'd think. You would think like that your book would say, well, the equation of an arbitrary line is this. Your book doesn't. It says the equation of an arbitrary line is this, which is true, but we don't think about it that way, right? And actually, and if we continued on with the way that the book did it, we wouldn't be able to do this cool thing that we're going to do in just a minute to verify what we get. You could, but it's not so obvious. The way we're going to do it is going to be obvious. Okay, so I need to change my coordinate system. I'm going to go from Cartesian coordinates into polar coordinates. And it's going to be the same object. The thing that you would get, like in the end, we're going to have r equals some junk of theta, right? This is what we want. We want to find r equals some junk of theta. That's what we're looking for. And in the end, it's going to look the same exact way. In fact, I wanted to go ahead and do that and say, okay, well, any line y equals mx plus b, you can think about it looking like that. If this is y equals mx plus b, then what point is this right here?
B.
B. And what point is this right here?
Negative b over m.
Yeah, good, right? Because what did you do? You set the y value equal to 0, knowing that this is x, knowing that this is y. You said, well, the y value there is equal to 0. So you bring the b over as a negative b, you divide by m, and you get the x by itself. You could also see if you plug that in there, the m's cancel, you get minus b plus b is 0. Yes, okay, we're good. Okay, so no matter what, it's going to look something like this. All right, the only difference is it's going to be written in r and theta. And the way we do that is we just use these transformations right here. We say, well, instead of x is equal to what? R theta, so m times r cosine theta. And what is y?
R sine.
R sine theta. There you go. But now, what we want is the r's all on one side. This is the same thing as if I gave you some jumble of stuff with x's and y's. You would say, well, get all the y's on one side, all the x's on the other. Here, that's what we want to do with r's and thetas. So there's a few different ways we could do this. We need to get the r's on one side, so I'm going to go ahead and choose to put them over on that side first. And so I'm going to get r sine theta minus mr cosine theta equals b. Now what would you do? What if I had this?
Oh,
Divided by r.
yeah. Take out the r.
Just 3, yeah, there you go. I don't want to divide by it, right?
Factor
Or
it out.
you just factor it out, right? There you go. And so r times,
When in doubt.
when in doubt, factor it out. There we go, right? Now what do we do? Want to get the r by itself.
So
Divide by
Divide
sine
by-
theta.
There you go. Right? Don't let the r's and the thetas confuse you. If that were a y and these were something of x, you would say, well, just divide by it. Right? And yes, that's what we're going to do. We're going to say sine theta comes down here minus m theta. All right, there you go. Your book is slightly different because it had the A's and the B's and the C's. Now we have this. But now check this out. So what this tells me is we have this thing. If I were so inclined, I could graph this. Like I could go to Desmos, choose a B, choose an M, or use sliders for B and M, and then like see what that thing looks like. I have no idea what it would look like.
do polar coordinates.
Yes, it does. And if you wrote this, r equals blah blah, and then with the theta you just type out theta, and then it turns it into this, so it knows. And yes, Desmos will do it.
And it will treat
Desmos
it
will
like
just-
Jekyll.
But what I'm saying is if I wanted to, I could on Desmos graph this as y equals b sine x minus m cosine x. And just like we did before, we'd find some funky thing. And then we could say, okay, that's what the funky thing does as I turn. And so I could turn and do all the funky things. This is what you're going to be doing. Don't laugh. You're going to be doing this soon. For the next homework set, that's exactly what you're going to be doing. But for this one, let's just check a few things. So let's think about it this way. When theta is equal to 0, what should the radius be? So notice it's back
0
here.
minus
To what? So remember, the radius is just the distance from the origin. And so when
Oh.
theta is
It would
equal
be
to
the
0.
square root of b squared. Right?
Well, wait a minute. So how far away
I
is
know.
this point from the origin?
Oh, negative b over here.
Yeah. And so think about it. If it were b over m,
Oh, okay.
it would be in the positive direction. But here it's saying go to the negative direction. So what I'm saying here is when theta is equal to 0, then r should be equal to negative b over m. Everybody buy that? Let's do another one that we could do easily. when theta is equal to pi over 2, then r should be, it should be b. When theta is equal to, what did I just say, pi over 2, then r should be b. Let's check those. Let's plug in a theta equals 0 into here and see what I get. B over sine 0, 0, minus m cosine 0.
So
B over what sine 0?
0 minus
0 minus
just n.
1.
M times cosine of 0 is,
1.
which is what?
Negative. So b. Negative.
Negative b over m. Hey, that looks good. Let's do it with pi over 2 and see if that works. So let's find out what is r when theta is equal to pi over 2. Cosine pi over 2. Okay, so what is sine pi over 2?
1. So 1 minus
1 minus, and what is cosine of pi over 2?
0.
So b divided by 1 is, lo and behold, yeah, it's looking good. So whatever this thing looks like in the Cartesian coordinates, like if I were to graph y equals b over sine x and cosine x, it doesn't really matter. What happens is this type of thing, right? It's so, and like I could, I mean, if I were so inclined, I could figure out that, okay, it starts here. Okay, so it starts here and then shoots way down and everything and must pop back up to infinity at some point. In fact, let's talk about that right here. Let's talk about this, because this is why I wanted to do it with m, y equals mx plus b, and not the way that they did it. So let's look at this. Clearly, if I'm doing this, and I'm finding, okay, like it starts here at minus bm, okay? And so then as I turn it, it moves like this, right? And I keep turning it and it moves like that. Eventually, I'm going to have some angle here. I don't know what that angle is necessarily, but it's going to be parallel, right? I'm going to have a parallel line. Now, let's just call whatever that is, whatever angle that is, I don't know what it is, but whatever angle it is that makes it parallel, let's give that a name. Let's call it phi. Now let's just say that phi is the angle that gives you a parallel with the line. Okay? Everybody with me on that? What is tangent of phi?
Right. Run over.
It's
No,
the
rise
one.
over.
It's the rise over the run. Good job. It is the rise over the run of this thing, isn't it?
Yeah.
Right? I mean, that's what it is. That's what rise over run means. It means that that's the same angle right there. Okay? So when they're the same angle, we're saying that that's at phi. So when you plug in the angle that makes them parallel, then tan phi is equal to m, which is the rise over the run. Yeah? Everybody buy that? Now watch this. If that's the case, then that means that sine phi over cosine phi is equal to m.
Yeah.
Right? Which means that sine phi equals m times cosine phi. Yeah?
And so
Which means that sine phi minus m cosine phi is equal to what?
0.
0.
And so when you're at that special place, like as it goes along, it starts off, when you're at 0, it gives you out, that function pops you out a minus b over m. And you're doing some stuff, and when you're up here, it pops out a b. But when you're equal, when you're at that special angle where it's that, it gives you r of phi is b, blah, 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 is 0 is infinite, which is exactly what you would expect, right?
Yeah.
How else could it be? Like, and you can see, like, yeah, it's going to, as you keep going,
Yeah.
it's going to give you this number, it's going to give you this number, it's going to give you that number, and then it's going to keep getting bigger and bigger, and huge and huge and huge and huge and huge, until when you're exactly parallel, well, it must be down at infinity, must it? The only way to do that is if that thing goes to 0 so that this thing blows up. But then once you've just passed it, well, it's going to hit up here somewhere, isn't it? And so it's going to do that, and then it kind of finally drops down to B, and then so on and so forth, and blah, blah, blah.
So like,
Yeah?
like tangent kind of. Like,
Yeah. Yep. Yep, you're going to get, and it's going to split, right? The same way that tangent does. You get a split so that you get closer and closer to it, it gets bigger and bigger. But then it drops down to infinity, right? Or negative infinity. I guess in this case it's going the opposite direction because it starts off with a negative number and it's getting negative, more and more negative and more negative. You could think about that kind of like as cotan. Cotan comes up like this and does that, right? And so as you increase, something's getting closer and closer to negative infinity until it blows up, and then the opposite thing happens. Now it's up here at positive infinity and it's dropping down from positive infinity. So, but yeah, the idea is the same. You'll notice it splits. Not everything that blows up splits like that. Like for instance, 1 over x squared doesn't split. 1 over x squared blows up the same way, right? But these guys, this happens too, but that's neither here nor there. So I wanted to do it that way because it's real easy to analyze that, right? Like, what is the thing that makes it parallel? Well, it's the tangent would be the rise over the run. That's M. Oh, yeah, that's how it could work. Because you see this and you're like, how could you possibly get a line that goes on forever? That doesn't make any sense to me. Like, how could it be that you're doing this stupid thing with the twirling? How could you make a straight line that goes on forever? Well, because it blows up. That's pretty cool. So, okay, questions on that? Okay, let's get into actual problems you're going to have. Okay, this is number 16. So can I get rid of all this stuff?
So on Desmos, is there just like a setting that changes it to polar coordinates and stuff?
If you just type in r equals junk theta, it will know. It will know what to do.
I feel like Desmos can do basically anything.
It does so much. It's great. It is excellent. So we're finding a polar equation with the same graph as this. This is number 16. Oops. So in other words, convert this to polar. Let's look at our handy dandy conversion chart here. Do you see anything that's like jumping out at you?
Just square root of both sides and then...
Well, you could do that. You could take the square root of both sides. That's one way of doing it. I was thinking like r squared. But watch what's going to happen if I do that. Like I say, well, r squared is that, right?
Yeah.
And so that's 2. But then you say, well, you're not looking for r squared. You're trying to get that thing by itself. So you take a square root, which is just what you said. 0. And there's 2 possibilities. Because you can have negative radii in polar coordinates. So either of those would work. And indeed, it would be the same thing. Like, what is this thing? It's a circle. And what's its radius?
2, but also negative 2. Like.
Yeah, root.
Root 2.
Right? Because we didn't, yeah, you see, that's what this is. Ah, right, that always messes you up. But it has a radius of root 2, so it does this, right? And it's like, well, but also, I mean, the negative one also works. But if I just told you that here's a polar graph. The radius is equal to root 2. You'd say, well, that would be the set of all points whose radius is equal to root 2. Because as you can see, it doesn't depend on theta. Just like if I told you to graph this. Y equals 2. What is that?
It's just a long.
It doesn't matter what value you put in for x, does it? Same way here. It doesn't matter what value you put in for theta. Because you say, well, wait a minute, this is y is supposed to be a function of x, and x isn't there. That means it's not dependent on x. No matter what your input value of x is, the output value is still 2. So this is your line. It's always just 2. Same thing here. You say, well, wait a minute. wait a second, like it doesn't, you don't have a theta. Well, that means that for every value of theta, the radius is root 2. Oh, okay, well that's just this thing then. Yeah. Everybody with me on that?
Yeah.
So how do we have to write that in like actual like
So if you just
parentheses
graph
and coordinates?
r equals
No, because that is the polar equation. It's r equals root 2. Or negative root 2. Okay? Now, you think, oh, that's not hard. Well, watch this. Number 26. Here's number 26. X plus 2 squared plus y minus 3 squared is equal to 13. Okay. Since we're running short on time, I'm just going to go crazy and just do this. Like, yes, that's a circle. Yeah, okay, that doesn't help you. Like, so what we're going to do is use our handy-dandy conversion formulae and say, well, if x is r cosine theta, then we have r cosine. And right now, since I'm pressed for time, I'm not going to write theta until the very end. This is r sine minus 3 squared equals 13. Notice this is not r sine theta minus 3. That's not what I'm doing there, right? That's r sine theta minus 3. So now when I square it, I get first outer inner last r squared cosine squared. Outer gives me a 2r, inner gives me a 2r, so 4r cosine plus 4. This gives me r squared sine squared minus 3, so how about minus 6r sine plus 9 is 13. You'll notice that 4 plus 9 is 13.
Oh, we can cancel.
So we could get rid of that. That's gone. And we have, now one thing I'm going to do is go ahead and collect the squares. R squared cosine squared plus r squared sine squared is the same thing as,
You could factor out
you could
R.
factor out, how you can factor out 2 r's from that.
and then that's just 1.
R cosine minus 6
Oh, yeah.
sine equals 0, like that.
So you just
So that's just 1. So this is just r squared plus 4r cosine. Anytime, I'm going to go ahead and tell you this, and this is for every class you take from here on out. Anytime you have sine squareds and cosine squareds show up in an equation, try to put them together. Because that's, if you could, and it may not be, right? That might have been 4r squared, and that might have been 3r squared, then you don't have it. But if they happen to be the same thing, you could factor it out, and it's equal to 1, and you just made your life a lot easier. Now we can factor out an r from the whole thing and say, okay, r is equal to r plus 4 cosine, 6 sine. Now that's equal to 0, so it's either the case that r equals 0, which is the most boring thing you could graph. That's just that. And so, yeah, okay, if r is 0, then that's true, but that's obviously not the case. So we're going to throw that away and then say, so then it must be the case that this thing's equal to 0. And if that thing is equal to 0, then this could be rewritten as r equals 6 sine theta minus 4 cosine theta.
Is R equals 0 the 0 vector?
We're not talking about vectors, but
Wouldn't it?
yeah. Yeah. So, but r equals 0, I don't think that works for here. Right? It doesn't satisfy this. And what you've done is you've just, well, you've squared a bunch of stuff, and squaring stuff gives you, well, I'm not too sure.
I don't
what's
think
going
r
on.
could equal 0.
No, you couldn't have r equals 0 in any of that.
R equals
Unless perhaps it happens to go
root
through the
13.
origin. I don't know.
R equals root
But
13.
I don't think that's... Yeah, r equals root 13, exactly.
Yeah.
So I think you're picking up an extraneous solution, something that's just not true. And just like, I mean, we've seen that before. Sometimes you get an answer that just does not work with your original thing. And in that case, you got to throw it out. And I think that's what's happening here. But this is true, and if you plug that into Desmos, you'll see that it's a circle of radius root 13 that's centered at minus 2, positive 3. Okay, let's hurry up. We got a lot more to do. So, now we're going to go in the opposite direction. Find an equation with the same graph as this. R sine theta is equal to -2.
Well, r sine theta equals
Oh, equals x.
equals y.
Wait, no. Y.
Equals y.
So
Okay.
it's just a line.
Oh, there you go. It's just the line and y is -2. And it's true, right? It works. And you can see this if you do the turning around thing, it works. It blows up in the right place and everything. Now, one thing you could have done to make your life really miserable is you could have said, well, I need to get the r by itself.
Oh.
And then you say, okay, well, that's root x squared plus y squared equals -2.
it's like
Sine
Over
would be y over r, which is root x squared plus y squared,
Looks like something
which is going to be -2
2
times root x squared plus y squared all over
Which is-
y. And then you could cancel this on both sides. And you get that 1 is equal to -2 over y, so that y equals -2. Or you could stop and say, anytime you have an r sine theta or an r cosine theta anywhere, your life's going to be much easier if you just do that. But if you just go for broke and you just plug everything in the way you see it, you'll get there. It's just going to be painful. Here's another example of pain. I didn't tell you which number that was, but this is what we're doing. So again, we're finding equations in x, y. So we're going from polar coordinates converting to Cartesian. This is 4. Yes, buddy. Well, you gotta wait just a minute, buddy. Real busy. First, secant is
You
what?
can use the tan, because that's one of the... Wait, no.
You could. Or you could say that
It's a one.
secant is the same as 1 over cosine. And so you have r cosine theta is equal to 4. So in
So
other words,
x
x
equals
is equal to
So
4.
it's
Or you can make your
up and
life
down line.
miserable
It's an up
and
down
say
line.
r equals, say again?
It's an up and down line. Like
You could say that's the same thing as x over r. Yeah, that's an up and down line, exactly. If x is equal to 4, then that means here at x you're equal to 4. And y is free. No matter what value of
so
y.
you plug in a 4 and you get in. You get out.
Well, you see, it's not really a function. It's not a function of y. It's a function of. I mean, it's a function of y. Y is the input, and x is the output. In this case.
Yeah.
But we're not talking about this. We're talking about you know what I'm saying? It's a little. The analysis is a little bit different. This is r as a function of theta. Perfectly good function there. And so you could do this, right? Which gives you r for x. R comes upstairs. 1 equals 4 over x. X equals 4, etc. And if you're really going to hurt yourself, you could have replaced the r with the square roots and wasted all that time writing the square roots. But what I'm saying is if you could identify, how could I turn this into one of these? There is a way of doing it, and you want to try to head in that direction if you can. You can't always. Now this is another thing, one of the reasons why, I'm telling you not to graph this time, because it tells you to do all of this and then use that to graph it. I don't care about that, because we're actually going to graph with polar stuff. And you might say, well, why would you ever do that? Like the first thing we saw was r was what, sine theta? No, we did cosine theta. And we said, well, you could just do some magic and turn that into x minus a half squared plus y squared equals 1/2 squared. That's what we did.
And so that's
Why don't you just do that and then graph it that way? What you're going to see, especially as you do this homework, is you're going to be given something like this, and the thing you're going to end up with is going to look like this. X plus 2xy squared minus 3x squared y equals 1. And it's like, yeah, graph that. Go, have fun. Just try to
plug in
graph it.
points.
Just plug in points and you'll be good. Whereas if you just graph it with the polar coordinates, it's much easier to do with polar coordinates. So there's a trade-off with everything. Do we have 2 more? Do we have 2 more? We have 2 more. We can do these real quick. Okay. Number 38. Okay, we have 3 more. Number 38. It is. It's your what?
I'm not gonna kiss it, you know why? Because I have some lip gloss on it and it's gonna make a mark on your
Whatever, no, I have no idea what I wrote there. I don't even know what that's asking me to do. Number 40. Oh, that's what it was. I'm sorry, 38 was r times 3 cosine theta minus 4 sine theta equals 12. Again, you could say, okay, cosine is x over r. R is that, so now you have x over the square root stuff. For y over the root stuff, and then you have the root stuff, and then, or you could say, wait a second, hold up, if I factor this in, I have my r cosine minus 4r sine. Always be looking for if you could change something into r cosine and r sine, because that's just x, that's just y, and I'm confident that you could figure out what that is from here. If you wanted to get the 4 by, what?
It's in the. Oh, wait, no. Oh.
How about a line?
I was thinking square.
Yeah, I know. It would be an ellipse. If it were squared, it would be an ellipse. Yes. Okay. I'm just trying to point out some pitfalls with all those last examples. 40. Okay, here we go again. R times R sine squared theta minus cosine theta equals 3. Now, do not think that that's just x squared, because it's not, right? This is like r sine, which is x times r.
No, times sine.
For
Yes, times sine. Yes, sorry, yes. And so,
Well, you can factor in the r.
bring it in. Right now you have
And then-
r squared sine squared theta minus r cos
which is
theta.
y squared plus x.
So it's
There you go.
minus
That's
the
that
parabola.
easy. Y squared minus x equals 3. So when you go from
Like a
there,
Is it a parabola?
it's a parabola.
A sideways parabola.
Sideways parabola. Exactly. Now instead of x being a function of y, y is a function of x. So you have your y squared minus 3 equals x. And so x input, this would look something like this. Yeah. And it should be going that way, yeah. Okay. Okay, 40. Now here's 44. This is the last one we got.
It's the hardest one.
Yeah.
The last one's always.
It's rough. Number 44. Okay, here we go. R equals 6 cotan theta. You know, and here's the thing, like, I'm not sure what they're looking for with this.
1 over tan and then use the tan.
Or
can you only do
No, you could.
Or
You
cosine
could.
over sine and then.
You could do that, and I think that's where I started. I said, okay, well, 6 cosine over sine, right? Cosine theta over sine theta. Okay. I mean, it's going to get ugly, right? I mean, there's really no way out of this, and some of them are just ugly. Like, we're going to say, okay, well, if cosine theta is x over r, I'm going to say, okay, so there's 6, this is x over r. Sine theta is y over r, which is the same thing as 6 times x over r times r over y. Yeah?
Yeah.
R's cancel. And just like you said, you could just replace it there and you'd be right. That's x over y. And so now you have r equals 6x over y, but r is equal to root x squared plus y squared equals 6x over y. Square both sides, should give you x squared plus y squared equals 36x squared over y squared. I guess you could keep going from there and say, okay, x squared y squared plus y to the 4th equals 36x squared.
Wait, plus.
Right? Yeah, I brought him upstairs.
Oh, yeah.
I said that, and that, and that. And I'm looking at this like, I don't know, I guess. Is that what they're looking for? I have to check the back of the book.
Factor out a y squared or complete.
You can't complete the square with that. Well, I guess you could, right? So 36.
I think you just factor out a y squared.
Right, and then you'd just be back up here where you had your y squared x squared plus y squared equals 36x squared, and now you can't get that into anything. So, I mean, and this is what I mean by like, good luck. You try to graph that, good luck. But in polar coordinates, this is not hard. Cotan, we know what he looks like. He starts up here, drops down, and does this. And you could actually do that. That's not too hard. And so I'm thinking this is some kind of line. But, or something, I don't know actually. But the point, so just check the back of the book and like you should try to get, if you have one that starts getting really ugly like this, just check at the back of the book and that might very well be what they're looking for, right? But just make your answer look like that. But this is the idea, some of them are going to be really bad. Turns out in polar, to graph them in polar, not that bad. Not that bad at all.
Good.
So, okay, guys, I think that's all I have.